0 to pi over 3. Okay, well, I guess I can just graph secant, and then I'm rooting this with the line y equals 4. Okay, well, I better then space out my business. So if that's 4, then that's the line y equals 4. And, well, secant of 0 is 1, and secant of pi over 3, okay, so picture kind of not to scale here, secant of pi over 3 is 2. So that's 2. So this is the graph of secant on the interval from 0 to pi over 3, that's 2. And therefore, if I'm looking for the region bounded by secant y equals 0, where x is on the interval from 0 to pi over 3, then the region being described is this one. It's just the sort of region underneath the y equals secant graph. Okay, great. Well, what am I supposed to do with that region? I am supposed to rotate it about the line y equals 4. So here's the line y equals 4. And, well, what happens when I rotate this region? Well, now I'm going to get up here at 8, sort of, there will be this kind of base, and then cha, and then cha-cha. So it's going to be something like that. Cha, cha, sort of zomp, zomp. Okay, the art might be kind of bad, in fact, just is bad, but what you're getting is some sort of, well, I don't know how to explain it. Kind of a cylindrical shape. It's just what you get when you rotate this green region about the line y equals 4. Well, what matters for us is that we need to find the volume of it. How? By slicing it vertically. And if we slice it vertically, then all of those shapes are going to be washers. Okay, so giving a little bit less explanation this time, here's my representative rectangle. What happens to that representative rectangle is when it gets rotated about the line y equals 4, we end up with a washer. And I need to know two things for that washer. I need to know the inner radius and the outer radius. So that's an arbitrary x value. And what is the inner radius of this washer? Well, the inner radius of the washer is just the distance from the top of the representative rectangle to the axis of rotation. And since that's 4 high and that's secant high, then this is going to be 4 minus secant. And then I need to know the outer radius. But, okay, the outer radius is just always 4. So that's all I have to say about that. Right? This distance is always 4. The distance from the axis of rotation to the bottom of the representative rectangle is just a constant for this problem. Therefore, I might be able to squeeze this in this one board. I'm going to take the outer radius squared, multiply by pi, so pi r squared gives the area of the big red circle, minus the area of the little red circle, so that's 4 minus secant. Take it back, I can't do this in just one board. I remember this problem now. So that's pi 4 squared minus 4 minus secant x squared times pi. So that is the that now gives the area of circle minus circle, so big circle minus little circle. And now I multiply that by the thickness, and we integrate from 0 to pi over 3. Okay, well, I can pull a pi out of this entire thing. So this is the integral from 0 to pi over 3 of 16 minus, when I square 4 minus secant, I get 16 minus 8 secant plus secant squared, cha, and, okay, so that's not too bad. I just get pi, integral from 0 to pi over 3 of 8 secant x minus secant squared. Okay, and because I've done this on like a million other videos, I think I won't go back into the detailed explanation of why everything is the way it is. I personally just know the formula for the antiderivative of secant. It's just 8 ln secant x plus tan x. And the antiderivative of secant squared is that was not what I thought was going to happen. 8 secant x minus secant. I guess I just convert that into tan or something.
Oh, Theo.
Whew. So wait, let me just do that now first. Wait, no. The derivative of tan is secant squared. Sorry, I lost it for a second. So 8 ln secant x plus tan x, and then minus tan. Okay, yeah. The derivative of tan is secant squared, and the derivative of 8 ln secant x plus tan x is, for complicated reasons, well, it's just 1 over secant plus tan, but it's back inside, and the back inside, makes it all work out. Just double check that formula by differentiating using the chain rule if you don't believe me, but it's just right. Okay, so what do we get? We get pi times, when I plug in pi over 3, well, this is 8 ln, secant pi over 3 is 2, and tan of pi over 3 is root 3, and then minus tan of pi over 3 is root 3. But then, when x is 0, tan of 0 is 0, secant of 0 is 1, but ln of 1 is 0, and tan of 0 is also 0. So those are all zeros. So, what we in fact get, if I did this all correctly, is pi times 8 ln 2 plus root 3 minus root 3. We can double check that, but that seems really right. 8 ln 2 plus 3 minus root 3. Yeah. Okay, good. Woo! 3 down. So many more to go. But I think there are some easy ones coming up. Okay. Don't stop now. #21 says, find the volume of the solid generated by revolving a region bounded by the graphs of the equations about the line x equals 6. Okay, so we're given x equals y squared and x equals 4, and we're rotating this whole thing about the line x equals 6. Okay, let's go. X equals 6, eh?
Theo, what are you doing?
Okay, x equals 4. Okay, so I guess I want to do this. I'm trying to plan out my space as I go. 1, 2, 3, 4. Hold on. I think I need this to go all the way out to 12. Whoa, Theo. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12. So x equals 6, 3, 4, 5, 6 is over here. That's the line x equals 6. X equals y squared is just a sideways parabola, but we're only going until x equals 4. So when I do that, I'll get 4, 2, so we get this. Okay. So all the effort here is in the drawing and thinking, I think. But if I interpreted this correctly, I'm supposed to find the volume of the solid generated by revolving the region bounded by the graphs of the equations. Okay, so the two equations were x equals y squared and x equals 4. Therefore, the region bounded by those equations is this region.
What are you doing, Theo?
Just playing with the big trash can full of poop. Okay, off camera there's a baby crawling through the room. Anyway, here it is. That is certainly the region. And what are we doing? Hi, Theo. What are we doing with this? What are we doing with this region? We are rotating this region about the line x equals 6. Okay, so when we rotate this region about the line x equals 6, what happens is we get this kind of type thing, and it's just like a zoom type shape. And so this is some sort of kind of flying saucer type shape with a sort of a hole drilled out of it kind of thing. Right. Yeah, this is the most accurate description. Okay, how am I going to find the volume of this? Well, once again, I need to slice it horizontally is the only reasonable way. And so I'm going to draw my representative rectangle. What does it look like? It looks like this. And what happens to that representative rectangle as it gets rotated about the line x equals 6, it becomes a washer. And we got an inner radius, and so once again it all boils down to finding the area of just this washer, and then if I can find the area of one, I add them all up. Alright, so what is the inner radius and outer radius of this washer? Okay, well, once again, I'm doing this with respect to y, because I'm rotating about a vertical axis, so my washer is going to be horizontal, perpendicular to that. So I have to sort of put myself in the frame of mind of, okay, I'm being given an arbitrary y value, and in terms of that arbitrary y value, I shall describe the dimensions of this washer. And okay, so I need to know both the inner radius and the outer radius of the washer. Well, the inner radius is just always 2, because the right edge of the representative rectangle is just always at x equals 4, so it's always 2 away from the axis of rotation. But the inner radius is, the outer radius is more complicated. And this is the curve x equals y squared after all. So what that means is, you give me a y value, and the x coordinate of the point on that curve is y squared. So it helps some people to actually like put a dot there and label that black dot y squared comma y. That's just what we mean when we say that the curve is x equals y squared. You give me a y value and the x coordinate of the point on that curve is y squared. Okay, well if that's the case, it means that this tiny distance from the y-axis to that point is y squared. But I want the purple curly braces, which is the distance from that point to the axis of rotation. And so that outer radius is 6 minus y squared. It's 6 minus the x coordinate. It's the x coordinate of the axis minus the x coordinate of the point on the parabola. Is another way of putting it. Is the distance from that point to the axis of rotation. Okay, so if you have all that under control, then we can just do it. You take 6 minus y squared, the outer radius, you pi r square it to get the area of the outer circle. You subtract the area of the inner circle, which is just going to be pi 2 squared. That's the area of the circle minus circle. And you multiply that whole circle minus circle by the thickness of the circle dy to get the volume of one washer, and then you integrate up the y-axis to get the sums of the volumes of all those washers. Okay, here since it's completely symmetrical, I'm going to be smart and go from 0 to 2 and then just double it because the parabola is totally symmetrical. Okay, so what do we get? We get 2 pi integral from 0 to 2 of 36 minus 12y squared, just not going to make that mistake again, plus y to the 4th, but then minus 4. I think I did that right. 36 minus 4y squared plus y to the 4th minus 4. Yeah. Okay, so this is really integral from 0 to 2 of y to the 4th minus 12y squared plus 32. And okay, this is just not too bad. It's just a polynomial. The numbers are not so, are basically nice. So that's y to the 5th over 5 minus up to 3 and divide by 3. So that's 4y cubed plus 32y. And this is being evaluated at 2 and 0. That's 2 pi. So that's 2 pi times 32 fifths minus, oh boy, 32 plus, I'm gonna call that 32 times 2 for the moment, and then I'm gonna pull out a 32. The zeros make it all 0, so this is actually 64 pi times pulling out a 32. 1/5 minus 1 plus 2, so just plus 1, so just 6/5 in fact. And so I guess this is 64 pi times 6 over 5, so whatever that is. 128, no, that's not a smart way to do it. What is that? Oh man, times 3 is like 192 or something. 180 and 12, 192, but then times another 2 is like something, whatever it is. 384 over 5. 384 pi over 5 is the answer. Maybe. That was number 21. Yep, it is. Okay, just working my way through this homework assignment at an extremely slow pace. Alright, 39. What is 39? 39 says, oh, I remember you. Use the integration capabilities of a graphing utility to approximate the volume of the solid generated by the region, blah, 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 blah. Okay, so, yeah. What do we get? This is kind of a die. I should have just not assigned this problem. Y equals arctan 0.2x. And what are we supposed to know? 2 arctan. 2 arctan 0.2x. Y equals 0, x equals 0, x equals 5. Y equals 0, x equals 0, x equals 5. Okay, so what does this look like? Well, it's going to look a lot like arctan. We want to find the region enclosed by y equals 0, x equals 0. In other words, we're in the first quadrant. And some arctan function, but we're going to go all the way out to 5. The arctan function has been stretched out vertically by a factor of 2, but then this 0.2x would probably be best understood if written as x over 5. So that means we are stretching this function out by a factor of 5. And so now by the time I get to 5, I'm where I normally am at when x is 1. Anyway, you can just plug in 5 there, and you get arctan of 1, which is pi over 4, so this goes to pi over 2. So that's pi over 2, and we're sort of halfway up the arctan. The asymptote will be pi, but that doesn't really matter. And what am I supposed to be doing again? Oh man, I bet I didn't leave enough space to like do what I was supposed to do. Use the integration cables we have to the volume of the solid generated by revolving the region bounded about the x-axis. Okay, good. So after reading this whole thing, I realized that this is the region under discussion, and I'm supposed to be finding the volume of the solid formed by rotating this region about the x-axis. And so, okay, throwback problem. This is actually just going to be a disk, not a washer. And what's the volume of this solid? Well, I draw my representative rectangle. This picture looks kind of bad. Something like that. That's a tiny bit better. So we get a washer. A disk. And the disk is determined by, well, it's going to be pi, this function, so 2 arctan x over 5, that squared, so pi r squared, will be the area of that circle, and then we multiply by dx, and then we integrate from 0 to 5. Okay, and that's all well and good, but we don't know how to antidifferentiate arctan squared. We don't even know how to antidifferentiate arctan. And so the thing you do is you just type this all into your calculator. I don't think we need to turn the camera around and all that kind of crap. but this is meant to be an exercise in you realizing that you can draw the picture, set everything up, do all the thinking, and then you can just type the integral into your calculator. In fact, if you're just really like dying as you're making it through this homework, you know, if you skip around a little bit here and there and just refuse to do an integral, the intellectual work is all in the setup. Anyway, this is totally right, and the answer is 15.4115 says the book, is what you get if you type this into GeoGebra or your graphing calculator. Okay, moving along, 47. All right, yeah, we did something like this in a previous video. So maybe this was now redundant. What is 47? It says, take the line y equals 1/2 x lying in the first quadrant is revolved about the x-axis. A cone is generated. And we're going from x equals 0 to x equals 6. So here's 6. If we, so that's 3, and that's just the line y equals 1/2 x, just fact. And the directions say, find the volume of the cone extending from x equals 0 to x equals 6. Okay, so this should sort of a little bit just blow your mind. Here we are going to do, in a couple of just simple lines of algebra and calculus, a problem that is just so difficult, what was once so difficult. And the answer is, we're going to take this line, the line y equals 1/2 x, we're going to consider the region underneath this line between, up until x equals 6, and we are going to revolve this region about the x-axis. And if we spin this about the x-axis, what happens is we get a cone. And what are the dimensions of that cone? Well, the radius of the cone is 3, and the height of the cone is 6. And so you could have sort of reversed engineered this equation to be the one that you needed. That's what we did on the previous video, to find the volume of a certain cone. Okay, well now we shall calculate the volume of the cone by just splitting it up into an infinite number of infinitely thin pieces. So we draw a representative rectangle, we and we just say, okay, this is just simply easy, right? I take a particular x value. What's the height of the representative rectangle? It's 1/2 x. I square that and multiply by pi. That gives me the area of that circular disk. I multiply by the thickness of the disk, dx, and I integrate along the y-axis from 0 to 6. And this should give me the volume of this cone. And so what we get is pi over 4, integral from 0 to 6 of x squared. That's pi over 4 x cubed over 3, but then evaluated at 6 and 0. Kind of don't exactly want to do that, but I guess I will. What do I get? I get 36, but then times another 2, so that's 72. And there we go, 18 pi. I'm sure that is right, and it is. And note that checks out with just what happens when you're like in middle school or whatever, and you say that the area of the base is so it's pi r squared h, so that would be pi 3 squared 6. So there we go. 1/3. Sorry. The area of a cone is the volume of a cone is 1/3 pi r squared h. So 1/3 pi 9/6 is indeed 18 pi. Okay, so what we've just done, okay, in this case we've done it with numbers, but we've just found there's this technique which takes 1 minute to find the volume of a cone. And that's kind of amazing because this cone is sort of this infinite object, and if you contrast this with the way we found the volume of cones like in middle school or even just, a month ago, it involved, probably involved just you memorizing the formula, but it involved knowing that a cone is really just kind of like a pyramid with an infinite number of sides, and pyramids have 1/3 the volume of the base. Well, why? Well, due to some complex argument involving how many triangular pyramids you can fit inside a cube, and there's this decomposition argument and these limiting cases, and there's a lot of just kind of baby calculus going on. But now, finding the volumes of like basic shapes now is just as simple as, can you write an expression for it in some kind of function we know how to anti-differentiate, and then we're just done. Okay, moving along, 49 and 50, which I think are linked. I thought I didn't assign all these problems, but I guess I did. Here we are. 49 and 50. Use the disk method to verify the volumes. Okay, so continuing in the exact same vein. I mean, this is like kind of an incredible, I think, moment of your life. You're going to find the volume of a sphere right now. All right, well. Let's go. Prove that the volume of a sphere is 4/3 pi r cubed. Okay, we begin. Well, what is a sphere? Oh, it is a solid of revolution, which is to say you can think of a sphere as being what happens when you can take a circle and you rotate it about the diameter. And so, what I will do is, I will take, I will take in fact just a quarter circle. Sure. I'll take just a quarter circle from, why does that look so bad? Anyway, it's not a good circle, but, and I will, yeah, that's r comma 0, that's 0 comma r, and I will shade this region here, and I will just say, hey, what happens if we rotate this region about the line y equals 0, about the x-axis? And the answer is we get a hemisphere. And the volume of that hemisphere is just half the volume of a sphere. So let's do it. Well, how am I going to do this? I just do the same old, right? Split this up into a bunch of rectangles. What happens to the representative rectangle? It gets rotated, and we get a disk. What is the area of a circle centered at the origin with radius r? Well, it's x squared plus y squared equals r squared. So I want this in the form y equals. So in fact, we get y equals root r squared minus x squared. Okay, so I take that radius, which is root r squared minus x squared, and I pi r square it. That gives me the area of the circle formed when that representative rectangle is rotated. And then, oh my god, and then I multiply by the thickness, and then I add them all up from 0 to r. And that will give me the area of a hemisphere, so I multiply by 2 to get the volume of the, that will give me the volume of a hemisphere, so I multiply by 2 to get the volume of the whole sphere. Okay, and then this is just not hard, right? Because you get 2 pi, integral from 0 to r. When you square the square roots, you just get r squared minus x squared. Now we have to be careful to remember that r is a constant for the sake of this problem, right? R is just the radius of the sphere that we begin with. It's not a variable. We're integrating with respect to x, so r is just a constant. So therefore, when it comes to anti-differentiating r squared minus x squared, this becomes r squared is just like a constant, so it's that antiderivative is r squared x minus x cubed over 3, but then evaluated at r and 0. So we get 2 pi times, this is r cubed minus r cubed over 3, and these are all 0, and so this is just 2 pi times 2/3 r cubed, and so this is just 4/3 pi r cubed. Whoa. The moral of the story is that with calculus, we can perform almost as just a kind of a routine little 3 to 4 minute exercise that's not even particularly challenging. We suddenly can prove with total clarity and complete confidence formulas which would require one to be some sort of genius if you lived in ancient times to come up with the formula for the volume of a sphere. With calculus, it's just a trivial little homework problem. And we can do things with calculus that we can't do, that we could not have done in ancient times, except perhaps with like extreme ingenuity. So take number 50, which is a follow-up on the exact same problem. Here's what it says. It's starting to get hard now. The problems are getting really hard and there's no picture associated with them, so you have to like read and think and understand. 50 says, a sphere of radius r is cut by a plane h units above the equator. Find the volume of the solid above the plane. Okay. Yeah, a sphere of radius r is cut by a plane h units above the equator. Okay, I got this. So here's what we have. We have a sphere, and then the sphere has radius r. So that's r comma 0. That's 0 comma r. And now what we're going to do with this sphere is we're going to slice it at a certain height above the equator. So take like, you know, the Tropic of Cancer, which I believe is the one in the northern hemisphere. Just take the line of latitude 60 degrees high, you know, which is quite high, and just cut that out. And what you're going to get is what's called, I believe, a spherical cap, I think is the name for it. It's the part of a sphere that you get if you just kind of slice a sphere along a latitude, along a certain latitude. Okay, so specifically our book says cut in there with a plane which is h high above the equator. Okay, and so what I'm now doing is I'm sort of drawing the circle and I'm drawing h, but I hope now that you recognize that in fact what we're doing is just taking what's left, right? Cut at the latitude 60 degrees point, say, of the Earth, and then just take everything that's 60 degrees or above. And so, in fact, you can conceive of this geometric shape, which was described in problem 50, as just what you get when this region, enclosed as seen here, is rotated about the y-axis. So, cha-cha. And I don't even need this other half of it, because it's just coming along for the ride. Okay, so pause for a minute and just agree that when that green shape is rotated about, well, I guess I could have just left it in there, because that's exactly what comes, right? When I do this, I get this spherical cap. Okay, alright, well, how do I find the volume of that spherical cap? Well, it seems that I should slice it. How? Horizontally. So I draw my representative rectangle, and here it is, and and that's an arbitrary y value, and now I have the equation of this circle, which is x squared plus y squared equals r squared. So what's the x coordinate of this thing? It's x equals root r squared minus y squared. Sorry, is that what I meant to do? Yeah.